Okay, so we're looking for the tangent line approximation of f of x to the square root of x at c equals 1. And I'm actually going to stop it right there because that's really the first part of what this question is asking us to do. So in order to find this tangent line approximation, so tangent line approximation, right, we're looking at L of x is equal to f of c plus f prime of c x minus c. And so we're given two pieces of information here that we're going to use to create this L of x formula. One thing that we're given is f of x is the square root of x in the original question. The other thing we're given is that c is equal to 1. Okay, so you'll notice that c pops up a couple of times within this question. We're going to replace that with 1, and then anywhere there's an f of x or its derivative, that's where this square root is going to come in. So if f of x is equal to the square root of x, we can also say x to the 1/2, right? That means that its derivative, so f prime of x, is 1/2 x to the negative 1/2, or its derivative is 1 over 2 square root x. Okay, we're going to use these two pieces. So again, we're back to L of x is equal to, so this is the function at 1, this is the square root of 1, plus the derivative 1 over 2 at 1, square root 1, times x minus 1. Now you can also do these two pieces off to the side, somewhere over here, totally up to however you want to set it up. But this gives us L of x is 1 plus 1/2 x minus 1. And so this equation on its own represents that tangent line approximation. Okay, so if you were to graph f of x is the square root of x, which would something like that, right? And if you were to graph this line as well, and I don't have a graph in front of me, but you can graph it, this would be approximately or very close to this graph at the point c equals 1. So it's not very far over. Maybe call this like 1 right there. So it's not very far over, and you could even go a little more specific. It would be at 1, 1, because f of 1 is 1. Okay, so this represents the linear approximation. Now what we want to do is use it to approximate the value of the square root of 1.1. Okay, so this is a second set of questions, or kind of like a part B, if you will. So now that we have this equation, we say the square root of 1.1, which would be comparable to f of 1.1, right, is approximately, not exactly the same, but approximately L of 1.1. So do you see how we're using this linear approximation to give an approximate value of the actual function itself? And then we just use this equation that we just found. So 1 plus 1/2 1.1 minus 1. So what we can do from there, it's really just cleanup. We get L of 1.1, or you can approximate square root 1.1 if you'd like, is equal to 1 plus, maybe let's say 0.5 times 0.1. So 1.1 square rooted is approximately L of 1.1, which is equal to 1 plus 0.05. So the square root of 1.1 is approximately L of 1.1, which is 1.05. Now, this is our approximate, or our approximation, your answer for this situation, and this is an approximation. On some of these, like this one, for example, you can find its actual value. Right, so you can actually find, by throwing on a calculator, what's the square root of 1.1. Calculator values, maybe we'll call this calculator. But this is about 1.0488088848. Okay, and you can see this is pretty close as far as function values go. So again, the idea behind this is you have the actual graph itself. So f of x looks something like this, right? This is f of x is square root 1. And we pick a convenient value. So say here at 1, 1, right? And there's going to be a tangent line that we're going to pretend actually crossed through at that point. This is L of x. So when it comes to 1.1, and again, we're really zoomed in for this. I can even really zoom this in. I think I can zoom this in. There we go. If we really zoom this in, make my dot a little bit better. Again, we're going to pretend that's tangent 2. But at 1.1, which is fairly close, right? This value right here, this is f of 1.1, which is the square root of 1.1, which we found on a calculator, 1.0488, and so on. However, what we were finding here on the line, and let me actually switch colors so we can see it a little bit better, but what we found here on the line, it's not wanting to do that. Green perhaps? What we found right here on this line, okay, this is L of 1.1, which we found to be 1.5. So we have this kind of balance between the actual function, that's the black line right here, the tangent line at a certain point, that's the pink line here, an actual function value, that's the blue, and then the tangent line value, which is green. And what we're doing is we're saying the green is approximately or close enough to the blue values. Now, if you did this again, but with farther away values, so here let's pick something out here. Let's pick like 2.5. Okay. So let's say f of 2.5, right? And let's use all the way up here. Hopefully we can see that okay. Let's find L of 2.5. Okay, myself a little more room. Okay, L of 2.5, use the exact same equation, 1 plus 1/2 2.5 minus 1. So if we simplify this, we've got 1 plus, I'm going to go with 0.5 again, and this is 1.5. And it's a little sloppy, but it's because I'm running out of room. So this gives us L of 2.5 is equal to 1 plus 0.75. L of 2.5 is 1.75. And that's this orange value right here. Okay, again, that's on the tangent line, the linear approximation value. Now, if we go to the actual value, that's back here on the black curve in the purple, this is just what's the square root of 2.5. Well, if we throw that on a calculator, I get 1.58113883. Now you'll notice that this orange value we had a moment ago is not quite as close to this purple value we just found. Not nearly as close as the blue and the green were to each other, right? That was our original question. The reason for that is this x value, this 2.5, is further away from our point 1, 1 that we used to make this equation at all, right? The whole equation for L of x, so L of x was, we used f of 1 plus f prime of 1 x minus 1, and it was all based on this x value down here, right? But the further away we get from this x value, 2.5, or even further away from that, some other points beyond on this curve, the less accurate this linear approximation gets. So what are other options? Well, you could just redo your linear approximation, right? I could do, there's not really, we like to work with kind of nice values. There's not really a good one closer to 2.5, but I could maybe do it at 4. I could, I can do it at any number that I want. I mean, realistically, I could do it at 2. It's just the idea behind the linear approximation is we work with quote-unquote nicer numbers that work with our function a little bit better. But by moving where this pink point is, by relocating this tangent line, it gives us less of a space between the actual function in the black down here and the tangent line in the pink above it. Okay? We have another example similar to this in just a moment.